So picking up with part 3, starting with problem number 7, a particle moves in v of r equals alpha r squared minus beta over r. Determine the A, conserved quantities, B, the effective potential, C, the circular orbit radius, D, the stability, and E, the frequency of radial oscillations. So this is a two-dimensional central force motion problem. So v of r equals alpha r squared minus beta over r. Our conserved quantities for a central force, E equals 1/2 m r dot squared plus L squared over 2 m r squared plus V over r. Our L is equal to mr squared theta dot. Our effective potential, V sub EFF of r equals L squared over 2 mr squared plus alpha r squared minus beta over r. So our circular orbit's going to satisfy dV sub EFF dr equals 0 and negative L squared over mr cubed plus 2 alpha r plus beta over r squared equals 0. So multiplying by r cubed here, we get negative L squared over m plus 2 alpha r to the fourth plus beta r equals 0, and 2 alpha r sub c to the fourth plus b r sub c minus L squared over m, that equals 0. So our stability is going to require here V sub EFF double prime of R sub C, sorry about that, that's R sub C, greater than 0. And V sub EFF double prime equals 3L squared over MR to the fourth plus 2 alpha minus 2 beta over R cubed. So using the circular orbit condition, V sub EFF double prime, R sub C, that's going to equal 8 alpha plus beta over R sub C cubed, and that's going to be greater than 0. So our radial oscillation frequency, that's going to be omega sub R equals the square root of 1 over m times the quantity 8 alpha plus beta over R sub C cubed. Okay, so that is number 7. And moving along to number 8 here. So number 8, 2 disks undergo a perfectly elastic condition. One is initially at rest. Given m sub 1, m sub 2, v naught, derive the final velocities, the scattering angle relation, and the maximum potential, maximum possible deflection angle. Okay. So collision in 2 dimensions. So just a note here, this problem is going to be undetermined unless a scattering angle or impact parameter is specified. So for a general result, we're going to use the center of mass coordinates. So for initial momentum, you get that P sub I equals m sub 1 v naught x hat. For a center of mass velocity, V sub cm equals m sub 1 divided by m sub 1 plus m sub 2 times v naught x hat. So our initial relative speed, V sub REL equals V naught. So for an elastic collision, the relative velocity rotates but keeps the same magnitude. So we're going to let the final relative velocity make this angle chi with original direction. So V prime sub REL equals V naught times the quantity cosine chi x hat plus sine chi y hat. So then from there, V sub 1 prime equals V sub cm plus m sub 2 divided by m sub 1 plus m sub 2 times V sub REL prime. So from here, V sub 1 prime equals V naught over m sub 1 plus m sub 2, bracket, this quantity m sub 1 plus m sub 2 cosine chi times x hat, plus m sub 2 sine chi y hat, close bracket. V sub 2 prime equals V sub cm minus m sub 1 divided by m sub 2 plus m sub 1 divided by m sub 1 plus m sub 2 times this V sub REL prime. So V sub 2 prime equals m sub 1 V naught over m sub 1 plus m sub 2 bracket this quantity 1 minus cosine chi times x hat minus sine chi y hat. So the scattering angle of the particle 1 satisfies this tangent theta sub 1. That equals m sub 2 sine chi divided by m sub 1 plus m sub 2 cosine chi. And the maximum deflection, that depends on the mass ratio. So if m sub 1 is less than or equal to m sub 2, the maximum can reach 90 degrees or more. If m sub 1 is greater than m sub 2, theta sub 1 max equals inverse sine of m sub 1 divided by inverse sine of m sub 2 divided by m sub 1. Okay, so that is number 8. And moving along now to number 9. So we have a rocket ejects fuel with exhaust speed u. Gravity acts downward. Mass loss satisfies this m dot equals negative gamma m. So we want to determine the velocity, the altitude, and the burnout velocity. So variable mass rocket. So the rocket equation with gravity, m dv dt equals negative u dm dt minus mg. And given m dot equals gamma m, m dv dt equals u gamma m minus mg. And dv dt equals u gamma minus g. So therefore, for here, v of t equals v naught plus quantity u gamma minus g times t. And if y of 0 equals 0, y of t equals v naught t plus 1/2 times the quantity u gamma minus g times t squared. Our mass here, m of t equals m naught e to the negative gamma t. So if burnout mass is m sub b, then m sub b equals m naught e to the negative gamma t sub b. And our t sub b is going to equal 1 over gamma ln m naught over m sub b. So our burnout velocity is going to be v sub b equals v naught plus quantity u gamma minus g times 1 over gamma ln of m naught over m sub b. So equivalently from here, v sub b equals v naught plus u ln m naught over m sub b minus g over gamma ln of m naught over mb. Okay, so that's part 3. Thank you very much and have a great day.